This airplane is about to break, and that's not a failure. That's the goal. Before a single passenger ever steps on board, this aircraft is pushed far beyond anything it will experience during normal flights. Wings are bent higher than they ever will be in the sky. Structures are loaded past their limits. Engineers don't stop the test when things start to look uncomfortable. They stop when the airplane finally gives them an answer. Because in aviation, a plane that never fails in testing is a plane engineers don't trust. In this video, we're going behind the scenes of aircraft certification to see how airplanes are deliberately pushed to their absolute limits, so that when you fly, those limits are never even approached. The test where engineers expect the plane to break in aviation, safety does not begin in the air. It begins with a simple but uncomfortable question. What happens when things go wrong? Engineers don't assume airplanes will always operate perfectly. In fact, aviation is built on the opposite assumption that systems can fail, materials can fatigue, and unexpected forces can occur. The goal is not to prevent failure entirely, but to understand it completely. That is why, before an airplane ever carries passengers, engineers intentionally push it until it breaks. Not accidentally, not unexpectedly, but deliberately under controlled conditions. To an outsider, this may seem counterintuitive. Airplanes are among the most complex and expensive machines ever created. Destroying one during testing sounds reckless. But in reality, this controlled destruction is one of the most important reasons commercial aviation is as safe as it is today. When engineers design an aircraft, they don't ask how much force it might experience. They calculate how much force it could possibly experience under the most extreme realistic conditions. This includes severe turbulence, aggressive maneuvers, heavy loading, and years of repeated use. From there, they add margin. A lot of it. Every airplane structure is designed around what's known as a limit load, the maximum force it should ever encounter in normal operation. But regulations don't stop there. Aircraft structures must typically withstand at least 150% of that load without catastrophic failure. This extra margin exists because the real world is unpredictable. Weather changes, conditions combine, materials age, aviation safety accounts for all of it. To verify these calculations, engineers don't rely on simulations alone. They build full-scale test articles, sometimes entire airplanes, sometimes complete wings, and mount them in massive test rigs. These rigs are equipped with hydraulic actuators capable of applying enormous forces with precise control. Slowly, the test begins. The load increases gradually. The structure responds exactly as predicted. And then, visibly, the airplane starts to change shape. Wings bend upward, the fuselage flexes, control surfaces shift slightly under stress. To a passenger, this would look alarming. But to engineers, this flexibility is a sign of a healthy design. A perfectly rigid structure would be far more dangerous. Flexibility allows an airplane to absorb energy, distribute loads, and avoid sudden, brittle failure. As the test continues, the load exceeds anything the airplane will ever see in service. At 100%, the structure must remain fully intact. At 120%, it should still behave predictably. Even at 140%, there should be no sudden loss of integrity. Then comes the critical moment. At ultimate load and sometimes beyond, engineers expect something to give. A crack may form, a component may yield, a structural element may permanently deform. When that happens, the test stops. And if the structure failed after meeting or exceeding the required safety margin, the test is considered a success. This is a key concept in aviation. Failure during testing is not a problem. It is data. Engineers are not only interested in whether something fails, but how it fails. Does the structure deform gradually or suddenly? Does it give warning before losing strength? Does the failure remain localized, or does it propagate dangerously? These details matter because real airplanes don't encounter forces one at a time. They encounter combinations of stress, gusts, loads, and fatigue acting together. Understanding how a structure behaves at its limits allows engineers to ensure that, even in extreme situations, the airplane remains predictable and controllable. For passengers, this testing happens quietly, far from view, but its results are visible every time you fly. When you look out the window during turbulence and see the wing flexing, you are not witnessing a weakness. But its results are visible every time you fly. When you look out the window during turbulence and see the wing flexing, you are not witnessing a weakness. You are seeing a structure operating comfortably within limits that were tested and exceeded, long before the airplane ever entered service. The wing you are watching has already been pushed far beyond anything you will experience on board, and it did exactly what engineers expected it to do. Aviation safety is not built on hope. It is built on evidence. And the philosophy that guides these tests is simple. Before nature can surprise an airplane, engineers will try to surprise it first. But breaking a wing in a laboratory is only the beginning. The real challenge comes when engineers try to replicate the chaos of the real world, from impacts to water, ice, and fire. That's where aircraft testing becomes even more demanding. Bird strikes, water, ice, and fire. Simulating the real-world breaking an airplane in a laboratory is only the beginning. Because while engineers can calculate loads and stresses with incredible precision, the real world does not follow equations. Weather is chaotic. Environments change suddenly. And nature has a habit of testing airplanes in ways no simulation can fully predict. That's why aircraft certification goes far beyond controlled structural tests. Engineers must prove that an airplane can survive the kinds of impacts and conditions it may encounter in everyday service, even when those conditions seem unlikely. This is where testing starts to look aggressive, not because engineers are careless, but because reality is. One of the most well-known and visually striking tests is the bird strike test. Birds and airplanes share the same airspace, especially near airports. Encounters are unavoidable, and while most bird strikes are harmless, engineers must prepare for the worst-case scenario. During certification, engines are tested by firing bird carcasses, carefully selected by weight and size, directly into spinning fan blades. The goal is not to show that nothing happens. The goal is to prove that when something does happen, the engine behaves in a controlled and predictable way. Blades may be damaged, components may deform, but the engine must not explode, shed dangerous debris, or lose containment. In many cases, it must continue operating long enough for the aircraft to safely land. The same philosophy applies to cockpit windshields. These are not ordinary pieces of glass. They are multi-layered structures designed to absorb impact energy while maintaining visibility and pressure integrity. During testing, bird strikes are simulated at high speed to ensure the windshield cracks in a controlled manner, without catastrophic failure. To the untrained eye, these tests look brutal. To engineers, they are reassurance. But birds are only part of the equation. Airplanes also have to contend with rain, hail, and ice, sometimes all at once. In testing facilities, engines are exposed to artificial storms. Massive volumes of water are sprayed into intakes to simulate heavy rain. Hail and ice are launched at critical surfaces. These tests are designed to answer uncomfortable questions. What happens if ice forms faster than expected? What if hail damages sensors? What if water disrupts combustion? Engines must demonstrate they can either continue operating safely or shut down in a controlled manner without cascading failures. Once again, the goal is not perfection. The goal is predictability. Another critical scenario engineers prepare for is water ingestion. During heavy rain or standing water on runways, engines may ingest significant amounts of water. Certification tests ensure that this does not cause sudden flameouts or structural damage that could compromise the aircraft during takeoff or landing. The most demanding phases of flight. In these tests, engines are deliberately flooded while running. Sensors, controls, and protective systems are monitored closely. Engineers want to see how the engine responds under stress, not just whether it survives. Because in aviation, survival is not enough. Control matters. Then there is fire. Fire testing is one of the least visible but most critical aspects of aircraft certification. Fuel systems, cargo compartments, insulation materials, and cabin components are all subjected to strict fire resistance and smoke toxicity standards. Engines are exposed to external fire sources to prove they can withstand flames for a required amount of time without catastrophic failure. Cabin materials are tested to ensure they resist ignition and limit smoke production. Why smoke? Because in many emergency scenarios, smoke, not flames, is the primary hazard. Certification standards focus heavily on giving passengers and crew time to react, time to evacuate, time to survive. These tests are not designed to look dramatic. They are designed to buy time when seconds matter. To viewers, these tests often feel excessive. Why destroy expensive equipment? Why test conditions that seem unlikely? Why push systems so far beyond normal use? The answer is simple: because the real world doesn't care about averages. Certification testing is not about what usually happens. It's about what could happen. Once, under the wrong conditions, at the wrong moment. Aviation safety is built around preparing for those rare moments long before they occur. There is also a psychological element to these tests. People instinctively react when they see expensive machines being damaged. It feels wrong, wasteful, even cruel. But in aviation, this discomfort is intentional. Engineers want to eliminate surprises. They want to see failure modes on the ground, in a controlled environment, with data recorders running and experts watching closely. Every crack, every deformation, every abnormal response becomes information. And that information feeds back into design improvements, operating procedures, and safety margins. This is why modern airplanes appear so calm in situations that feel chaotic to passengers. They've already faced worse, on purpose. What all of these tests have in common is not destruction, but discipline. Nothing is random. Nothing is theatrical. Every test has a specific question behind it. Can the airplane remain controllable? Can systems fail without cascading? Can passengers be protected long enough for procedures to work? If the answer is yes, the airplane moves one step closer to certification. If not, the design goes back to the drawing board. And yet, even after all this physical testing, impacts, storms, fire, the airplane is still not considered proven, because physical damage is only half the story. In the next part, we'll look at what happens when systems begin to fail, not because of impact, but because of complexity, and why airplanes are designed assuming that something, somewhere, will eventually stop working. Failures are expected. Why airplanes are designed assuming systems will fail. After all the physical testing, bending wings, firing birds into engines, exposing airplanes to water, ice, and fire, it would be reasonable to think the hardest part is over. But in many ways, this is where the most important testing begins. Because airplanes are not just structures, they are systems. And systems, by their nature, eventually fail. Aviation engineers do not design airplanes assuming everything will work perfectly. They design them assuming that something, somewhere, will eventually stop working. This idea may sound unsettling at first, but it is one of the core reasons modern aviation is so reliable. The philosophy behind failure-based design. In most consumer technology, failure is treated as an exception. Devices are expected to work, and when they don't, the result is inconvenience. In aviation, failure is treated as an expectation. This approach is known as failure-based design. Instead of asking, how do we prevent failures? Engineers ask a more difficult question. What happens when failures occur? And how do we keep control? Every critical system on an aircraft is designed with this mindset. Engineers assume components will break, sensors will give incorrect data, computers will disagree, and power sources will be lost. The goal is not to eliminate failure entirely. That would be unrealistic. The goal is to make sure that no single failure, or even multiple failures, can lead to a loss of control. One failure is not an emergency. Let's start with a simple case. If one system fails on an airplane, it is rarely considered an emergency. That's because critical functions are not handled by a single component. They are distributed across multiple independent systems. Lose one, another takes over. This is why you'll often hear that airplanes are redundant. But redundancy in aviation is not just duplication, it is layered independence. Systems are designed to be physically separated, powered differently, and controlled by independent logic. The goal is to prevent a single cause from disabling multiple layers at once. What about 2 or 3 failures? Certification doesn't stop at single failures. Engineers must demonstrate that the airplane remains controllable even when multiple systems fail simultaneously. This includes combinations that are statistically unlikely, but still physically possible. For example, loss of a primary flight computer combined with a sensor malfunction, failure of a hydraulic system along with an electrical bus, incorrect data combined with degraded automation. These scenarios are not hypothetical. They are actively tested. During system certification, failures are intentionally injected. Sensors are disconnected. Computers are shut down. Power sources are removed, all while monitoring how the airplane responds. The expectation is not that everything keeps working as normal. The expectation is that the airplane degrades gracefully. Graceful degradation. This is a key concept in aviation. When systems fail, the airplane does not suddenly become uncontrollable. Instead, capabilities are gradually reduced in a predictable way. Automation may step back, alerts may appear, workload may increase, but control is preserved. In some cases, pilots transition to manual or alternate control modes. These modes are not improvisations. They are trained, tested, and certified. Manual flight is not a backup of last resort. It is a fundamental part of the system. Pilots are trained to fly without automation, without flight directors, and without certain protections. The airplane itself is designed to remain stable and controllable, even in these reduced configurations. The backup computer is not one computer. There is a common misconception that airplanes rely on a single primary computer with one backup. In reality, there are often multiple levels of redundancy, sometimes using entirely different architectures. For example, primary flight computers, secondary or alternate computers, independent monitoring systems that cross-check outputs, mechanical or analog backups for critical indications. These systems are designed not just to back each other up, but to disagree safely. If two computers disagree, the system does not blindly choose one. It flags the inconsistency, alerts the crew, and transitions to a safer mode of operation. This is why disagreement is not considered failure. Silences. What certification tests actually prove. During certification, engineers must demonstrate that the airplane behaves correctly under defined failure conditions. Not just that it keeps flying, but that alerts are clear, failures are isolated, pilots are not overloaded, and recovery remains possible within certified limits. What regulators are looking for is not perfection. They are looking for predictability. Failures are not surprises. They are part of the plan. The bigger picture. When people say aviation is safe, they are not saying airplanes are flawless. They are saying airplanes are honest. They reveal their problems. They provide options. They give time. And that philosophy, expecting failure instead of denying it, is one of the strongest foundations of modern aviation safety. In the next part, we'll look at flight testing, where real airplanes, real pilots, and real risks come together before certification is ever granted. The flight test campaign, the most expensive test flights in aviation. By the time an airplane reaches the flight test phase, it has already survived years of analysis, simulations, and ground testing. Wings have been bent, engines have been abused, systems have failed, on purpose. And yet none of that is enough, because there is only one place where all of those systems truly come together. In the air. This is where the flight test campaign begins. One of the longest, most complex, and most expensive phases of aircraft certification. Who test pilots really are. Test pilots are not simply experienced pilots. They are engineers in the cockpit. Many test pilots have backgrounds in aerospace engineering. They understand not only how to fly the airplane, but why it behaves the way it does. Every movement, every vibration, every delay in response is data. Unlike airline pilots, whose goal is smoothness and efficiency, test pilots are trained to do the opposite. They deliberately push the airplane toward its edges, not recklessly, not impulsively, but methodically. Every maneuver is planned. Every parameter is monitored. Every flight is followed by hours and sometimes days of analysis. Flying. Outside the comfort zone. During flight testing, airplanes are flown far outside the conditions passengers will ever experience. Test pilots explore extreme angles of attack. They test handling near aerodynamic limits. They fly at minimum and maximum speeds. They evaluate performance with degraded systems. Some flights are dedicated entirely to finding where the airplane becomes uncomfortable, and then going a little further. These are not dramatic stunts. They are slow, incremental steps. Engineers want to understand exactly how the airplane behaves as it approaches its limits, not just where those limits are. Testing controllability. One of the most important questions in flight testing is simple. Can the airplane always be controlled? This includes situations where automation is reduced or disabled systems have failed. Control laws are degraded, environmental conditions are unfavorable. Test pilots intentionally fly the airplane in configurations that demand precise handling. They assess how much control authority remains, how predictable the response is, and how much workload is placed on the crew. An airplane does not need to be comfortable in these conditions. It needs to be honest. Predictable behavior allows pilots to respond correctly, even under stress. Why this takes years? A full flight test campaign can involve thousands of flight hours and multiple test aircraft. Different airplanes may be configured differently to focus on specific areas: performance, systems, avionics, or handling qualities. Flights are repeated again and again under slightly different conditions. Why? Because certification is not about proving something once. It's about proving it consistently. A single successful flight proves very little. Regulators want to see repeatable behavior across a wide range of scenarios. They want evidence that the airplane responds the same way today as it did yesterday, and will continue to do so years from now. This is one reason airplanes often fly for years without passengers. They are still learning. The cost of certainty. Flight testing is extraordinarily expensive. Every test flight involves specialized crews, telemetry teams on the ground, engineers monitoring real-time data, support aircraft and infrastructure. Each hour in the air costs tens of thousands of dollars, sometimes more. And yet manufacturers willingly accept this cost because uncertainty is far more expensive. A flaw discovered in service is not just costly, it damages trust. Flight testing is where potential problems are exposed quietly, methodically, and long before the public ever sees the airplane. No shortcuts. Allowed flight test programs are not flexible timelines. They end only when the data is complete, not when schedules demand it, not when marketing wants it, not when impatience sets in. Every required test point must be flown. Every anomaly must be understood. Every unexpected behavior must be explained or corrected. This is why flight test aircraft often look different from production airplanes. They may be covered in sensors, probes, and markings. Their job is not to look finished. Their job is to tell the truth. Antoine, why this phase matters so much. Flight testing is where theory meets reality. It's where engineers stop asking, should this work? And start asking, does it work in every time? An airplane that passes flight testing is not just capable, it is understood. And that understanding is what allows pilots, airlines, and regulators to trust it with millions of lives over decades of service. One final step remains. Even after thousands of hours in the air, the airplane is still not approved to carry passengers, because flying the tests is not the same as proving compliance. In the final part, we'll look at certification itself, the documentation, reviews, and decisions that determine whether an airplane is allowed to enter service at all. Certification and why it takes years. Why one test can delay a plane for years. After years of testing, on the ground and in the air, an airplane may look ready. The wings flex the way they should. The engines behave predictably. Systems fail gracefully. Test pilots have pushed it far beyond anything passengers will ever experience. And yet even now, the airplane is still not approved to carry passengers. Because in aviation, flying the test is not the same as passing certification. Certification is not a performance. From the outside, certification can seem frustratingly slow. Airplanes appear capable long before they are allowed into service. Test flights are completed. Demonstrations are successful. And still, no approval. That's because certification is not about proving that something can work. It's about proving that it will work every time, under clearly defined conditions for years to come. Regulators are not impressed by spectacular demonstrations. They are interested in documentation, repeatability, and traceability. In aviation, proof is not a video. It's a paper trail. The role of regulators agencies, like the FAA and EASA, are often misunderstood. They are not there to design airplanes, and they are not there to promote manufacturers. Their role is simpler and stricter. They verify that every requirement has been met, every assumption has been validated, and every risk has been accounted for. This includes reviewing thousands of pages of documentation covering design decisions, test results, failure analyses, and operating limitations. Certification is less about flying and more about understanding. Understanding how the airplane behaves, understanding what happens when things go wrong, understanding where the boundaries are, and how clearly they are communicated. Where documentation matters more than demonstrations. An airplane can perform flawlessly in a test flight and still fail certification. Why? Because a single successful demonstration proves very little. Regulators want to see how systems behave across many repetitions, how results change with small variations, how failures are detected, isolated, and communicated, how procedures guide crews when automation steps back. Documentation is how this understanding is preserved. It ensures that safety does not depend on individual expertise or memory, but on a shared, verifiable body of knowledge. In aviation, if it isn't documented, it doesn't exist. How one sensor can delay an entire program. One of the most confusing aspects of certification for the public is how something seemingly small, a sensor, a line of code, a minor discrepancy, can delay an entire airplane program. The reason is not that the part itself is critical. It's that the assumptions behind it are. If a sensor provides incorrect data, regulators don't just ask whether the airplane can handle that failure. They ask, how often could this happen? How is it detected? What else depends on this data? What does the crew see? What decisions might be influenced by it? A single unresolved question can ripple through multiple systems and procedures. Until every connection is understood, certification pauses. Not because the airplane is unsafe, but because uncertainty still exists. Why slow equals safe? In most industries, speed is rewarded. In aviation, caution is. Certification moves slowly because it is deliberately resistant to pressure. Schedules, market demand, and competition are not allowed to override unanswered questions. This can be frustrating. It can be expensive, but it is intentional. Every delay represents a decision to resolve uncertainty before it reaches passengers. In aviation, time is used as a safety tool. What passengers rarely realize. From a passenger's perspective, certification is invisible. You don't see the years of review behind a flight. You don't notice the operating limitations that quietly shape how airplanes are flown. You don't hear about the procedures that were rewritten dozens of times before being finalized. What you experience instead is predictability. Flights that behave the same way, day after day. Systems that respond consistently. Crews that are trained for scenarios that almost never occur. That consistency is not accidental. It is certified. Why trust comes from boredom. There is a saying in aviation that captures this philosophy perfectly. If it looks boring, it's probably safe. Certification is full of rules that passengers never notice, limits that are never reached, procedures that are rarely used, redundancies that remain invisible. These rules exist not to impress, but to protect. They are the reason flying feels routine. The final perspective. When people ask why aviation is so safe, the answer is not a single technology, system, or innovation. It is a mindset that assumes failure, that demands proof, that values documentation over demonstration, and that is willing to wait years to remove uncertainty. Every airplane you board has been delayed, questioned, challenged, and scrutinized far more than you might imagine. And that's exactly why you can trust it. Every boring rule you never notice is the reason flying is this safe.